Hey y'all, Dr. Grossman here. In this video, we're going to go through one more example of a complicated equilibrium calculation that's going to involve the quadratic equation. In this case, we are given a reaction where we have hydrofluoric acid, an aqueous compound, reacting with water, a liquid. We end up with aqueous fluoride and aqueous hydronium. And we're told the equilibrium constant. It's small, but we know it. We're also told that we have 1 millimolar of HF dissolved in water. Our task is to determine the equilibrium concentration of hydronium, and you're specifically told to report it in micromolar units. So we know initial information, we want equilibrium information, so as you might guess, let's start with the ice table. Okay. So I know that I can ignore water, it's a liquid. Before I get really going, I want to note that this concentration is in millimolar, and we should never put anything other than molar or atmosphere into our ice tables. So let's start by converting this to molar. So 1 millimolar, 1 millimolar is 10 to the minus third molar. Right, the metric prefix milli always means 10 to the minus third. So here we have 1 times 10 to the minus 3, or 0.001. Okay, so I'm going to go ahead and put 0.001 in my ice table. I don't have anything else to start. I lose reactants. I gain products. This is a simple example in the sense that coefficients are all 1, so it's minus x plus x plus x. 0.001 minus x, x, and x. Okay, so we now have our equilibrium expressions for each of the individual reaction substituents. We know that our equilibrium constant is equal to the concentration of hydronium, concentration of fluoride, divided by the concentration of HF. We can conveniently ignore water. Okay? So we have 3 terms, we have 3 equilibrium terms. Let's go ahead and plug them in. Our value of 7.6 times 10 to the minus 4th is our equilibrium constant. This equals x and x, so x times x is x squared, divided by the concentration of HF is 0.001 minus x. Going through the algebra reasonably quickly, I'm going to move 0.001 minus x over to this side. I have 7.6 times 10 to the minus 4th times 0.001 minus x equals x squared. Okay, distribute into the parentheses. I have 7.6 times 10 to the minus 7th minus 7.6 times 10 to the minus 4th x equals x squared. Rearrange it so everything's on the same side. 0 equals x squared plus 7.6 times 10 to the minus 4th x minus 7.6 times 10 to the minus 7th. My A is 1, my B is 7.6 times 10 to the minus 4th, and my C is minus 7.6 times 10 to the minus 7th. So A equals 1, B equals 7.6 times 10 to the minus 4th, and C equals 7.6 times 10 to the minus 7th, negative. Okay, let's go ahead and use the quadratic, and I'll switch colors here. Okay, so for the quadratic equation, we know it's negative b, so negative 7.6 times 10 to the minus 4th plus or minus the square root of b squared minus 4 times a times c. Remember there's a negative sign there. All over 2a, and a is 1, so all over 2. Okay, so we have negative 7.6 times 10 to the minus fourth plus or minus the square root of b squared is 5.77 times 10 to the minus seventh minus 4 times a times c, so it's plus 3.04 times 10 to the minus sixth all over 2. Okay, this simplifies to negative 7.6 times 10 to the minus fourth plus or minus the square root of 3.62 times 10 to the minus sixth over 2. The square root of 3.62 times 10 to the minus sixth is 1.9 times 10 to the minus third. So we end up with negative 7.6 times 10 to the negative fourth plus or minus 1.9 times 10 to the minus third all over 2. Okay, so at this point, we have our plus or minus. You just need to put this in your calculator, and you'll see the two possible solutions for x are equal to 5.7 times 10 to the minus fourth. That's if you use the plus. Negative 1.33 times 10 to the minus third, and that's if you use the minus form of it. Okay? As we saw in the last video, only one of these values is going to be physically possible. What I want to note here is that both fluoride and hydronium have equilibrium concentrations of x, which means x must be positive, it can't be negative. So this is not possible. This is the value of x. Okay? And that's quite convenient because x is the equilibrium concentration of hydronium. That's what we were looking for. But this is in molar units. We want it to be in micromolar. So the last step here is to convert to micromolar. 5.7 times 10 to the minus fourth molar. We want micromolar. It's in molar. So remember, 1 goes to the prefix. The conversion factor is 10 to the minus sixth. This ends up being 570 micromolar. So at equilibrium, the concentration of hydronium is 570 micromolar. The concentration of fluoride is also 570 micromolar. And if you wanted to, you could figure out the concentration of hydrofluoric acid by taking 0.001 minus this value. Okay, so that's really it. That's all of the types of calculations we can see when working with equilibrium. In all cases where you're given initial amounts and equilibrium amounts, you need to find some way of figuring out x. The three ways are: if you are explicitly told an equilibrium amount, you can always solve for x. If you are told a total pressure and you have gases in your reaction, then you can solve for x. Or if you don't know either of those two things, but you do know the equilibrium constant, you can use the quadratic equation and solve for x. All of these are viable strategies. Some are just a little bit more belabored than others.